so much more time, but I'm gonna do. I wanted to definitely do a follow up uh, on the QCAT paper, the quantum assisted design thing. So I basically, if I pull out my notes from last time, the understand VQD. So I think I did on the video at the end sort of a bit of the XXI coupling gate, and in the meantime. Some of the authors of the paper actually reached out and said they are open for helping me answer questions and stuff like that, which I really appreciate. I want to go through some of this stuff solo first because I think that's what helps me learn, and I think what's going to help people watching this as well enjoy the experience more. But I'll definitely get in touch with the group. I think there's a lot to do there. I want to start taking a sneak peek at VQD and what is this and how is it different from VQE. So, and probably there was a reference on the paper, quantum assisted design or something like that. If I just search for that, will this actually? Yeah, quantum aided design. That's the paper. So if I take a look at VQ, if I search for VQD, there's nothing in here. Oh, wait a second. That's not the paper. That's the one for the optics hardware. I want the one for it's probably this one. VQD. Here you go. So the inversion quantum deflation algorithm. 52 of excited states. Let's take a look at this. So is this going to be anyhow findable in archive? Excited states. That seems to be the paper. Did I click on it? I clicked on it. Someone. This is VQD. Here we go. Let me make my face smaller. Let's fly through the paper. See if, before that, let me pause for a second because I want to just make sure. I'm freaking out these days that my sound is on, because it happened that I did a 1 hour session without any sound, and that cannot happen again. So I'm kind of having a little widget app here that tells me whether my microphone is working. I'm going to pause this for a second. You won't notice though. So back in here, that makes my face lighter as well. It's like almost like having an actual lamp in here. So what is this about? The calculation of excited state energies of electronic structure Hamiltonians has many important applications, such as the calculation of optical spectra and reaction rates, while low-depth quantum algorithms, such as the variational quantum eigenvalues solver VQE, have been used to determine ground state energies. Methods for calculating excited state currently involve the implementation of high-depth controlled unitaries or a large number of additional samples. Here we show, okay, so there's, I don't know, here we show how overlap estimation can be used to deflate eigenstates once they are found, enabling the calculation of excited state energies and their degeneracies. We propose an implementation that requires the same number of qubits as VQE and at most twice the circuit depth. Our method is robust to control errors, is compatible with error mitigation strategies, and can be implemented on near-term quantum computers. Estimation used to deflate eigenstates. Okay. So there's the algorithm in here, and then there's some mathematical proof and detailings. Error accumulation, discussion, sampling cost, destructive swap test, and that's the overlap test. the Hadamard overlap test. MIMK mod 2. So there is a better way to do that than what I'm using for the VQLS thing. It's a modular multiplication. Okay. What's from numerical simulation? I think I can show my. Okay, the references. I want to take a look at the algorithm itself. Try to understand the diagram first, maybe. Let's go all the way up. So, what have we got in here? So R prepares these from fiducial state 0. Expectation estimation of, I don't know what is P1, P2, and Pn, and overlap estimation. Then classical adder calculates the overlap of, so they're calculating the overlap of something. Lambda 0, lambda k, lambda 1, lambda k. Okay, so there's a lambda k that's prepared. I don't know what those lambdas are. And then classical adder calculates the actual expectation value of the Hamiltonian. And then there's an optimizer that updates lambda k, which I guess is a set of angles, okay, to minimize. And there's a cost function that is the energy for this set of angles plus the overlap. Okay. Plus how much overlap. So there seems to be two components to these. Let me see if I can get my. I'll pause for a second. Should click on here. Whatever, I'm having some issues again with a pen, but that's what it seems to do. So why, I don't know. Probably have to read the text, but it's some expectation estimation and then some overlap. But this expectation, is this going to be the classical? Is this just what VQE does, or what's the essential part in here, or what's the let's see. I'm gonna skip the intro for now. Maybe maybe it should help though. But form the spectrum method, because there's some eigenvalue problems are ubiquitous among science engineering. Google's PageRank algorithm alone has had a significant impact on modern society, and at its core solves an eigenvalue problem associated with the stochastic matrix describing the World Wide Web. Another important example is principal component analysis, which is widespread application in bioinformatics, neuroscience, image processing, etc. The time-independent Schrodinger equation provides yet another example of fundamental eigenvalue problem. Its numerical solution enables properties of atoms, molecules, and materials to be predicted, with far-reaching applications in materials design, drug discovery, etc. Characterization of excited state energies of molecules is required to predict charge and energy transfer processes in photovoltaic materials, or to understand some chemical reactions such as however classical methods such as density functional blah, blah, blah. Okay, quantum computers have the potential to solve these and other problems significantly faster than they know. Quantum error correction. Okay, the variational quantum eigensolver introduced in reference 30 is the first algorithm designed to find the lowest eigenvalue of a Hamiltonian on a near-term non-fault tolerant quantum computer. VQE is based on the variational principle and utilizes the fact that quantum computers can store quantum states using a actually fewer resources than required classically. VQE uses parameterized quantum circuits to prepare trial wave functions and compute their energy. In a classical computer, to find the parameters minimizing these energy. The low circuit depth of VQE has led to, since its introduction, modification has been suggested to enable VQE to find excited state energies. For example, the folded spectrum method, which requires finding the expectation of the squared Hamiltonian with quadratically more terms, or symmetry-based methods, which are non-asymmetric. Okay, I know anything about that. Such suggestions have been more recently superseded by two proposals: a method that minimizes the von Neumann entropy and the quantum subspace expansion method requires the large number of high-depth controlled unitaries, and the quantum subspace expansion method requires a large number of additional. Okay, we can dive into those examples maybe later as a curiosity as well. Our algorithm extends VQE that's what I thought. It kind of extends VQE to systematically find excited states at almost no extra cost. We achieve this by adding overlap terms into the optimization function. Okay, so it's as simple as adding overlap terms. In order to exploit the fact that the Hermitian matrices admit a complete set of orthogonal eigenvectors, exploiting further the fact that VQE retains the classical parameters of ansatz states that enable their repreparation. Low-depth quantum circuits can then be readily used to calculate these overlap terms. I'm not sure I understand that. So in VQE, the real parameters lambda for the ansatz state are classically optimized with respect to the expectation value of this Hamiltonian, which is decomposed by using these. Okay, now it's not working. Come on, it's not working at all. I hate that my pen doesn't work. I mean, I spent 20 years on this, so it's not a big deal. Okay, we know this. Our method extends VQE to calculate the kth state by instead optimizing the parameters for the ansatz state such that the cost function is really, so that works. You just add the overlap, but what's the overlap here? What is this calculating? You're minimizing the overlap. So you want something orthogonal to what? What is lambda I? Okay, so the kth excited state by inserting the parameters for the state, such as the cost function, is minimized. This can be seen as minimizing the energy subject to the constraint that lambda k is orthogonal to the states so it's orthogonal to, and what are these? All the other ones? So lambda 0 would be, then actually we show how choosing sufficiently large means the minimum of Fk is going to do with the energy of the kth state, provided the answers. So does this mean that you first find the lowest energy and then you find an orthogonal one? So you're kind of finding the next one, and then you do this over and over again. That would be cool. That is a genius idea. If this is the well, the first term can be used in the key. The second term is the sum of overlaps of the ansatz state with states 0 to k minus 1 and can be computed efficiently in a quantum computer using one of the methods given in section 4. So computing that requires knowledge of lambda 0 to lambda k minus 1. And so an iterative procedure is required to calculate the kth eigenvalue. That's what I just said. Yeah. Okay. First lambda 0 is calculated. Okay, we're done with VQT. We're done. It's nice. I like it. That's damn smart. Come on. Instead of something kind of fancy, it's like just let's iterate more. Okay, so you calculate the lowest energy and then using VQE by minimizing E. then lambda 1 is this is genius. Then it's so simple. The concept, I mean, I guess it's probably tricky, but I mean, how to come up with that? It's minimizing, because the idea is that because they are the eigenvalues, they're all orthogonal to each other, right? For K1, then K2, but how do you find? So how do you consider the overlap? How do you do that? So how do you consider? How do you accumulate? How do you make sure that it's orthogonal to all of those? Because the first iteration seems easy to me, but how do you do that for example? Because if you want to find for K3 or for K2, you want something orthogonal to both K0 and K1, right? Schematic for original inflection is in figure 1. Shell gas is a state preparation circuit. Computer then use the results. It's going to, okay, so we know this. What was the figure? Why is this scrolling so bad? Sorry, that's the classical optimize updates to minimize. How do you calculate these? How do you make sure that when k is bigger than 1, you're the overlap? Now that I know the overlap test makes so this destructive test makes it easier to understand the whole concept here. So, but how do I make sure that it's orthogonal to all of the previous ones? That's the point here. The circuit is used repeatedly to compute each of the expectation values and overlap terms for I lower than k. The overlap terms are computed using circuits from section 4. Let's go to section 4. A low depth method for estimation. I mean, I know using the trial state preparation circuit followed by the inverse of the preparation circuit for the ith previously computed state. The overlap is a low depth method for overlap estimation proposed in the reference 12 can be seen by writing the overlap as so you're using this. Wait a second. So you're using you're just making sure that it's orthogonal to the previous one you found? How does this guarantee you that you don't find another one? Because you're always minimizing, or what? Because R is the circuit that is is your ansatz, right? The overlap is estimated with precision by the fraction of all 0 bit strings when measuring this state, the computational basis. So these are true eigenstates with possibly non-distinct energies. This method requires knowing the inverse of the preparation circuit for each previously computed state. While this inverse is often known in theory, by inverting gates and the composition of the original preparation circuit, device errors may mean that the implementation is inaccurate in practice. If we define to be the optimal parameters originally found to prepare the ith state using VKD, then its inverse can be found by fixing these and varying the trial state parameters so that the overlap is maximized. This technique enables you to retain the robustness to control errors that is characterized. Okay, this I don't get much. Why do you need the inverse? As you're not minimizing for Your minimizes the expectation value of the overlap. Why do you need the inverse? The overlap doesn't require the inverse. Okay. Well, it does if you don't want to have double the amount of qubits, right? Because you would literally have to have the double amount of qubits to do that destructive. So in this mutation, it requires the same number of qubits in the run as VQ and around twice the circuit. In appendix, we will describe an alternative method. Okay, that's same circuit depth as VQ, but twice the number of qubits because you're doing the destructive swap test. Okay. So this is another. So what was described in here? So I just skipped all this stuff. Okay, so what's described in here? No, in here, this is another method. Okay, that the overlap equals these, and so this is what's in reference 12. In reference desperation, reference 12. It's a nature. Okay. What? Not gonna buy. I'm gonna pay for this. Let me see. Cool. So, but I'm happy with the alternate method. I just want to understand intuitively what's going on. But I think I've got it already. So, VQD requires this. Okay, so the subtest requires double amount of qubits. If a larger gate depth is available, then then you can actually do phase estimation. It can be used to reduce the total runtime of overlap estimation. So you have different techniques in here to calculate these. So can you calculate alpha QP? What is alpha QP? Is this like a what is alpha QP? Is this a thing actually? 40. A reference 40. Accelerated version of quantum eigensolver. April 2019. Stuff is really recent. That's so cool. Oh, I had it open already. It's alpha VQE. I like the name alpha VQE. Tunable Bayesian QP, alpha QP. Okay, these I probably might want to take a look at that. Quantum phase estimation on steroids. So let's see. Alpha QP and alpha VQE. Interesting. For runtime, numerical simulation. We simulated VQD on that's hydrogen or what? And the estimated basis for a range of internuclear separations and compared it to exact diagonalization, as shown in Figure 2 using So this is the example. They run an example. There's a discussion on error accumulation. In general, we cannot assume perfect state preparation. Suppose. Okay, but I think I got the basic idea. I will deep dive into this probably later on. I just want to make sure that I kind of go back to the other paper, to the original one, about the simulation and that stuff. Okay, but I get the gist of it. So it's the idea is you use VQE to compute the lowest eigenstate, and then you kind of change your cost function to consider kind of minimizing the overlap between that state and sort of the next step right? Okay, but why? And the next, so your the next eigenstate you're looking for, yeah, because that means that it's, if you're minimizing the overlap, it means that it's orthogonal, and you do that iteratively, and so you're getting all the, you can get up to, kind of basically get all the different eigenstates. Yeah, I get it. I think it's I'll dive into these probably later on, but it's choice of effective Hamiltonian, because there's a lot of nuance, I guess, to the Hamiltonian you choose, and or how do you do all this stuff, sampling cost, and then the destructive swap test, and these, we know about these, but I also want to dive into maybe this part, because maybe I could use that actually for my other project. What is these? It's the bitwise product, I guess that's what it means, is it? Because then you should use, maybe that's, how do I, is it the bitwise product? How do I, methods for numerical simulation, bounds for error accumulation, error mitigation, symmetry constraints. Okay, we'll dive into the error correction part later, error mitigation part later. I just wanted to know, where is these post-processing explained? Probably somewhere here. Figure 4. The swap test enables the overlap of two states to be determined in precision. Repeating measurements after applying a circuit or quantum register in the state. While the original swap test acting on two n-qubit states required an ancilla in a control swap state, leading to that the same outcome distribution can be attained more efficiently without an ancilla using parallel Bell basis measurements. So that actually has a name. It's a Bell basis measurement. Well, yeah, it makes sense because it's a Bell basis measurement, so it's telling you whether they're both zeros or not. Actually, that makes sense. It's a Bell basis measurement. Interesting. So in classical logic, the so-called destructive swap test shown in figure 4 requires just two n qubits in depth. Okay, but they don't explain it. That's the post-processing is just that, and then 1. And so if this is 1, but it's not 2, right? So you're really only going to get I don't know. I'll maybe there's another way to find that. What is the post-processing in here? But I'll deal with this in the other video. Anyway, I get the gist. I think the idea is I think I know enough to just go back to the original paper here, the actual simulation stuff. So I can tick that off the list so far. So that's done. What else is done? This is done. And this is for later. And so I think there's no advantage into using an MS gate versus a control Z gate, but I want to understand a bit more why is that enough. Those are different types of, I mean, the MS gate is native to an ion trap computer. That's also one in the email that I got from the authors, they mentioned that. and kind of makes sense. But I don't know if I'm happy with this explanation. So, but I think my next would be to understand the design of the ansatz a bit better. Yeah, good. It was better than I expected, to be honest. I thought I would have a harder time with this. So I'm happy. Cool. I hope you enjoyed the video.